Hello everybody and welcome back to Advanced Functions. Today we will be looking over chapter 1.3, which is equations and graphs of polynomial functions. First we'll cover the factor form of a polynomial as well as symmetry. In the symmetry subtopic we'll have even functions and odd functions. So let's begin. The factor form of a polynomial. The zeros of a polynomial function y equals f of x correspond to the x-intercepts of the graph and to the roots of the corresponding equation f of x equals 0. If a polynomial function has a factor x equals a that is repeated n times, then x equals a is a zero of order n. When we consider that, we have when n is odd, the graph crosses the x-axis. However, it goes straight through for n equals 0 and is like a little squiggle for the rest. However, when n is an even number, then the graph just bounces off the x-axis. You can see those two examples here. Even an odd polynomial function. An even function is the one where if the exponent of each term is even, then the whole function is even. An even function satisfies the property f of negative x is equals to f of x for all x in the domain of f of x. An even function is symmetric about the y-axis. An odd function is one where if each term of the function has an odd exponent. An odd function must satisfy the following property. F of negative x has to equal negative f of x for all x in the domain of f of x. An odd function is rationally symmetric about the origin. Examples. Let's look at these. Determine whether each function is even, odd, or neither. Explain your thinking. Okay, so the first one, we could see that the exponents are 6, 2, and 0, which are all even. Next, we must check whether or not f of x equals to f of negative x. We know if we substitute negative x, that would still become a positive, and here wouldn't matter. Therefore, it would still be the same exact thing. Therefore, this has to be an even, function. The second one, g of x. G of x is equals to negative x cubed plus x. Again, we could easily see that both of the exponents are odd. And so now we have to perform the test. If we were to put negative x, we would get negative x cubed, which would be a negative. So a negative x cubed times negative 1 would be x cubed. Let's look at g of x. G of x is equals to negative x to the power 3 plus x. We see here that if we were to put in negative x, we would get negative x cubed, which would be positive x cubed, plus negative x, which would be negative x. Therefore, we would have x cubed minus x. Now, if we did the negative of the full function, we would have positive x cubed minus x. So, we have proven that this function is odd since it satisfies the property of f of negative x is equals to negative f of x. I will let you try h of x by yourself. As always, the solutions will be posted in these little YouTube videos. Now let's look at this part. Without graphing, determine if each polynomial function has a line of symmetry, point symmetry, or neither. Okay, So what we have learned is that if it is an even function, then it should have line symmetry. If it is an odd function, then it should have point symmetry. So let's try this one out. Let's try f of x. So we have negative 2x to the power 4 plus x to the power 2 plus 7. Inputting negative x, we would get the exact same function. Therefore, that function is even. Therefore, this should have a line of symmetry. For this one, we have 5, 3, and 1, all odd. So we need to input negative x and negative f of x. Again, we could quickly do that. Here we'd have a negative, so we have positive 4x. Here we have a negative, so negative x cubed. And here we have a positive 6x. So 4x to the power 5 minus x to the power 3 plus 6 of x. If we were to take the negative of this whole function, then we would have the exact same result. Therefore, this is an odd function and should have point symmetry. Again, try h of x by yourself. If you're wondering how these would look graphed, I will show you in just a moment. Okay, so here are all the examples graphed. So this is the first example of f of x. We could clearly see that it is symmetric and that if we took negative f of x with negative x, we would have x to the power of negative x 6. Honestly, let's just do this quick and just put negative in front of all the x's. I can't believe I messed that up. Kinda sad. Okay, let's go. I guess it doesn't like that. We see that they are the exact same function, therefore this is an even function. Let's continue with example G. This is G. We see that it looks pretty odd. It has a little squiggle in the middle. So again, let's do the same thing. If it's odd, then it should be the same for negative x. Negative. And then negative. There you go. And then we need negative g of x. So let's post that in. There you go. So let's compare these two. We can see they're the exact one, therefore this one has to be odd. Let's continue onward. We have h of x, which looks like this. It's a really big boy, so you could tell. So let's zoom back in. We could see that it has a square and then a cube, but we should still try both of the tests. So the first one, this is f of x. Then we have f of negative x. And then negative f of x. We see that all three of them are different, therefore this function is neither. For part B, we had to figure out whether or not they have point symmetry, line symmetry, or none. So let's do that quickly. Here, again, we just do the tests of whether or not it is odd or even. So let's do that. Negative x. I think just do that. Maybe? No. There you go. Negative x, f of x, the exact same function. Therefore, this is even. And as you can see here, it is perfectly symmetric about the y-axis. However, let's look at G now. G, we see it's a little squiggle. So we have to prove that it is an odd function first. So let's do that quickly. Negative. Come And then last one, well, we know this is going to be a positive. There you go. This is with g of negative x. Now let's do negative g of x. What do we get? We get that these two are the exact same function. Therefore, this is an odd function, and it has point symmetry around the origin. We see this part equals that part, and so we're really happy with that. Lastly, we have h of x. This is what it looks like. So let's figure out whether or not it is symmetric. We have negative x and this one we know is going to be a plus, and then we need to do the negative, and then just, well, we could see h of x. So from here we see that again none of them are the exact same, therefore it is not symmetric around the origin, and it is not a odd or even function. And that's about it for this part. Now that we've finished the examples, let's move on to the homework, which for today is the following questions. They shouldn't be that difficult, so I will go over them in a couple of moments. As always, we will start off with rather simple questions that you could probably do in your head. So let's start with question 1. For each polynomial function, state the degree and the sign of the leading coefficient. Describe the end behavior of the graph of the function and determine the x-intercepts. So let's quickly go over this. For A, we see that the degree of the function has to be the sum of all the orders of the x-intercepts. Therefore, we have the order of 1, 1, and 1. Therefore, this is a third degree function. The sign of the leading coefficient is nothing here, therefore it has to be positive 1. So it is positive. Describe the end behavior of the function. Since we determined it is a third degree and it is positive, it has to go from quadrant 3 to quadrant 1. Okay, let's look at the x-intercepts of f of x. So clearly, to find the x-intercepts, we just need to make f of x equal 0. In order to do that, we need to make each of the factors equal 0. Therefore, the x-intercepts have to be 4, negative 3, and 1/2. Okay, let's move on to b. G of x is equals to negative 2, x plus 2, x minus 2, 1 plus x, and x minus 1. Okay, so what is really important with these sort of questions is always pay attention to things like this. For example, if it was 1 minus x, you could rewrite that as negative 1 times x minus 1. Therefore, that could easily change the reflection of the graph. But since we have 1 plus x, we could just rewrite it as x plus 1, and we're all good. So let's do the degree. We have 1, 1, 1, and 1. We have 4 ones, therefore the degree of the function is 4. The sign of the leading coefficient, as you can see, is negative. Now, the end behavior of the function could be found using the two things we just discovered. So we said it is 4th degree and then negative, so it has to go from quadrant 3 to quadrant 4. Now, the x-intercepts are really easy. We have negative 2, 2, negative 1, 1. C. Let's speed run this. Degree of the function, 2 plus 1 plus 1 plus 1. That's 5. Degree of the sign of the leading coefficient, positive, since we have nothing here. So the end behavior would have to be going from quadrant 3 to quadrant 1, because it's odd and positive. And then the x-intercepts, here we have to pick the 0, so negative 2 divided by 3, so negative 2/3. 4, negative 1, and this is 2/3. Oh, sorry, no, this is 3/2. Lastly, p of x is equals to this. The degree would be 3 plus 3, which is 6 degree. Sign of the leading coefficient is negative, so it goes from quadrant 3 to quadrant 4. The x-intercepts are negative 5 and 5. Now let's move on to 2. For each graph, do the following. State the x-intercept states the interval where the function is positive and the intervals where it's negative. And 3, explain whether the graph might represent a polynomial function that has zeros of order 2 or of order 3. Okay, so let's see. X-intercepts are negative 4, 1/2, negative 4, negative 1/2, and 1. The intervals where the function is positive between negative 4 and negative 1/2, and then when it is greater than 1. And then the negative ones would be when it is less than negative 4, and in between negative 1/2 and 1. Lastly, explain where, orders of 2 or 3. That is the bounce and the squiggle. Here it passes straight through, therefore it has no zeros of order 2 or order 3. Part B. X-intercepts are negative 1/2, negative 1, oh my god, and then 4. It is positive nowhere, and it's always negative. Except we can't say it is negative at the x-intercepts, but I think you should know that by now. And lastly, whether or not it has a degree of order 2. Here we have a bounce, here we have a bounce, therefore yes it does, it has 2 of them. C. X-intercepts, negative 3 and 1. It is positive when it is less than negative 3 and when it is greater than 1. And between negative 3 and 1 it is negative. It has, this is straight through, so that's not an order 2 or order 3. This is a squiggle, so it could have an order 3 at 1. Sorry if it's a little bit too fast. Lastly, we have x-intercepts once again, negative 5, and then 3. It is greater when it is. It is positive when it is greater than negative 5, when it is between negative 5 and 3. And that's it. And it is negative when it is greater than negative 3. It could have a bounce at negative 5, which means it might be in order 2. Here it passes straight through. So that is it. Let's move on to 3. I said 1 and 4. Okay, determine the zeros of each polynomial function. Indicate whether they are of order 1, 2, or 3. Okay, for 1, as you can see, the zeros of f of x would be 3, negative 2, and then 3 divided by 4, 3/4. Then order 1, 2, or 3, all of these have a exponent of 1, therefore these are all order 1. Okay, and then 4, we have negative 6, 5, and then 2/3. And we have, this is of order 1, this is of order 2, this is of order 3. Really easy. Determine algebraically if each function is even or odd. Okay, well, again, we just substitute negative x for all of them, and then negative f of x, which I will show you in a moment. Okay, so let's find if this is odd or even. So if it is even, then we have f of x is equals to f of negative x. Let's find what f of negative x is. So f of negative x is equals to negative 2 negative x minus 3, negative x plus 2, and then 4 times negative x minus 3. This is also equal to negative 2, and then we could remove the negative 1 from here. X plus 3. Here we can remove the negative 1 and get x minus 2. From here, it is negative 4 minus 3. Again, we could remove the negative 1, which we would get 4x plus 3. Let's move all the negative 1's together. We know that we have 1, 2, 3 negatives, which would still make a negative. And then we have another one, which would make a positive. So we have 2, x plus 3, x minus 2, 4x plus 3. So that does not equal f of x. Therefore, it is not odd. Sorry, not even. Therefore, not even. Let's try f of negative x. Oh, sorry, negative f of x is equals to negative 2 times x minus 3, x plus 2, x minus 3, which is equals to 2, x minus 3, x plus 2, and then 4x minus 3. Again, we could see that these are not the same as f of x or f of negative x. Therefore, it is not an odd function either. Okay, well, let's look at example 4. We have the following function, p of x. So again, we need to find what p of negative x equals. So let's do that. 3, we substitute negative x's, plus 6 times negative x minus 5 squared, 3x minus 2 cubed. Let's expand this. So we have negative x minus 6. Then this would be negative 1 times x plus 5 all squared. I think I'm missing a bracket. There we go. And this is, oh, I forgot the negative x. There we go. This is negative 1 again times 3x plus 2 cubed. Let's expand this. So what do we have? We have negative 3 x minus 6. Then we have negative 1 times x plus 5 all squared. We could rewrite this as, negative 1 squared x plus 5 squared, negative 1 cubed, 3 plus x power 2 cubed, which is all equal to, this becomes positive, this is negative 3 x minus 6, x plus 5 squared, 3x plus 2 to the power 3. We could see that these two functions aren't the same, therefore it is not even. Let's see if it's odd. So negative p of x is equals to just the negative of that. Quite honestly, we know it's just going to be negative 3x plus 6 because we're just multiplying the first term by negative. 3x minus 2 cubed. Again, we see that none of these equal, so it's also not odd. Let's look at question 5 now. So question 5 is the following. Determine whether each function is even, odd, or neither, and explain without graphing, determine if each polynomial function has a line of symmetry about the y-axis, point of symmetry about the origin, or neither, and then explain. Okay, so I assigned A, C, and E. Well, let's quickly go through these. Let's do this, honestly. I feel like it will make more sense. A. Y is equals to x to the power 4 minus x squared. So we see these are two positives that are, sorry, not positive, these are two even numbers. So let's just test if it's an even function. So let's say f of negative x, because we could say this is f of x, is equals to negative x to the power of 4 minus negative x to the power of 2, which is equals to x to the power of 4 minus x to the power of 2, which is the same, therefore it is even. Then it's asking if it has a line of symmetry or a point of symmetry or none. Well, since we determined it is an even function, then it has to have a line of symmetry about the y-axis. So let's do C now. Y is equals to negative 4x to the power 5 plus 2x squared. We had this is an odd, this is an even, so technically it shouldn't be even or odd, but again, let's just check. F of negative x is equals to negative 4 times negative x to the power 5 plus 2 negative x to the power of 2, which is equals to negative 4 times negative 1 to the power of x to the power 5 plus 2x squared, because this will be a positive. It's equals to 4x to the power 5 plus 2x to the power 2. These two don't equal. So now let's just do negative f of x, and we get 4x to the power of 5 minus 2x squared. None of them equal, therefore neither. That's the best handwriting I could do. Since it's neither, it shouldn't have a point of symmetry nor a line of symmetry. So let's move on to part E. Part E is a little bit long, but that's okay. Negative 2x to the power 6 plus x to the power 4 plus 8. So again, these are all even because this is a power of 0. Let's just check if it's even. If it is, then we're good. F of negative x is equals to negative 2 negative x to the power of 6 plus negative x to the power of 4 plus 8 is equals to negative 2 x to the power of 6, because this becomes a positive and this becomes a positive still, so x to the power of 4 plus 8, therefore even. Again, that means it would have a line of symmetry about the y-axis. Let's move on to question 6 now. So in question 6, it asks us to determine an equation for the polynomial function that corresponds to each graph. That shouldn't be too difficult, because let's do this. It's quite fun. I assigned B and C, so 7B. What do we have here? We have a couple of x-intercepts at x equals to negative 3, x equals to negative 1, and x equals 2, and then when f of 0 is equals to, what is that, 6? This should be 12. Well, there we go. Those are the important things to know. Well, we know that the way to write a polynomial function would be f of x is equals to a, where this is the leading coefficient and the leading, this is the leading coefficient, and then this is x minus something, let's say b, x minus c, blah 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 blah. So in here we know that f of 0 is equals to a, and then we know what the factors have to be, since we know the x-intercept has to be x plus 3, x plus 1, and then x minus 2. Again, since it's f of 0, this just equals to a of 3 plus 1 minus 2, which is equals to negative 6. A is equals to 12, so a is equals to negative 2. Therefore, the equation would have to be is f of, well, it's an equation, right? Yeah, equation. So let's just write it. Y is equals to negative 2 x plus 3 x plus 1 x minus 2. Now let's do the same thing for C. Where did my, there it is. 7C. Again, let's write out all our x-intercepts. So we have x is equals to -2, x is equals to 1. The important part here is that we see that these parts are squiggles. Well, these ones went straight through. Therefore, since, oh, not squiggles, sorry, bounces. Since they're bounces, these two should be of order 2. Let's just put a little 2 to remember. And then we have when x equals 0, y is equals to -12. Let's see when x equals 0. So again, let's write this. We know the function would have to be written as y is equals to a, and then our factors, which is x plus 2, and then since we said it's a bounce, squared, and then x minus 1, again, squared. From here, it is rather simple. Since it's -12, we substitute that in, is equals to a, and what those are when x equals 0, so we'll substitute zeros in, so we have 2 squared, -1 squared. So -12 is equals to, this becomes 1, and this becomes 4, to 4a, so a is equals to -3. Since a is equals to -3, we could now write the equation, which is y is equals to -3 times x plus 2 squared, x minus 1 squared. And that's it for this question. Let's go to question 12, which is the last one. There it is, 12. Determine the zeros of each polynomial function, state whether each function is even, odd, or neither, and verify your answers algebraically, and finally sketch a graph of each function. Okay, let's do that. Twelve. A. Let's move this a little bit. There you go. So what do we have? We have f of x is equals to x to the power 4 minus 13x squared plus 36. Well, immediately what we have to do is factor this. We could tell that this seems like a square of some sort because this is x to the power 4 and this is 6 and this is in the middle of -13. So let's try and factor it. For example, I feel like it has to be x squared minus 6. Actually, let's see. What else can we do? So let's try to factor it. We have something that multiplies to 36 and adds up to -13. That could be, for example, what do we have? We have 6 and 6, which would be -12. We could have 4 and 9, which adds to 13. So there you go. These are the two we have. X to the power 4 could be written as x to the power 2 squared, which is wonderful, because now we could just do x minus 4 and then x minus 9. There you go. Let's continue factoring these because we know that this could be, there you go. These could be expanded further. This is the difference of two squares. So we have x minus 2, x plus 2, x minus 3, x plus 3. Okay, now that we have factored it, we know that the zeros of this function would have to be when x equals 2. Let's just write them all in those. -2, 3, -3. You should probably organize them in an increasing order, but I don't think it's necessary right now. Now let's state whether this function is even or odd. We have all to the power of 1s, so this is the 4th degree, but again, let's just quickly check using our newfound tool. F of -x would be -x minus 2, -x plus 2, -x minus 3, and then -x plus 3. We'll remove all of the negatives from here. It should be 1, 2, 3, 4. I'm just going to do -1 to the power 4 times x plus 2, x minus 2, x plus 3, x minus 3. This becomes a positive 1, so this is technically our answer. A little bit too lazy to write all of it over again, but that is our answer. If we compare it to our f of x, it is the exact same. Therefore, this is an even function. Happy face. Sketch the graph of the function. Okay, well, this is a little bit more difficult, but we don't have to get fully into the complications over here. All we know is that we have our beautiful graph. It intersects at -3, -2, at 2, and then at 3. We could find what f of x equals to at 0, so f of 0 is equals to 2 times -2, -4 times 3, -12 times -3, 36. Hopefully I'm right. Just give me a second. Seems like I am. So let's go. It's 36. Then we know that this is a 4th degree with a positive leading coefficient, so it's going to be going from quadrant 2 to quadrant 1. So we will have something across the lines of this. Actually, let's see this. Oh my. Just pretend that it is going through all of them. Although that should. I know this is really annoying, guys, I'm sorry. Straight lines. Touch that. Yes, you did it. Now pretend that these are symmetrical. Completely the same, okay? Then we're good. Now let's do part 2, and we're done for today. So what do we have? We have g of x is equals to 6x to the power 5 minus 7x to the power 3 minus 3x. Let's do that now. We have that. We have to factor it again. So here we could immediately remove the x's. So we have x, 6 to the power 4 minus 7 to x to the power 2 minus 3. What can we do about this? It has to multiply to -18, then add to -7. We could do 9 and 2, so -9 and 2 plus, yep, so let's do that. Is equals to x, 6 x to the power 4 minus 9x squared plus 2x squared minus 3 is equals to x. Let's factor out the 3 and then the x squared, 3x squared. So we'd have 2x squared minus 3 plus 1, 2x squared minus 3. Missing a bracket. There you go. And now what we have is x, 3x squared plus 1 times 2x minus 3 squared. Okay, there you go. We need to find the zeros of this equation. So first, we know immediately that x is equals to 0 because that is the first term. Then we have 3x squared plus 1 is equals to 0. So then 3x squared is equals to -1. So x squared is equals to -1/3. So x is equals to the square root of -1/3. Which I don't think we could get, can we? So this one is out of the question. Then we have 2x squared minus 3. 2x squared minus 3 is equals to 0. 2x squared is equals to 3, x squared is equals to 3 over 2, x is equals to square root of 3 over 2, plus and minus. That's what we have as our roots for now. Let's go on. Now we have to check whether or not this is even or odd. So let's do that quickly. Again, f of negative x is equals to negative x 3 negative x squared plus 1, 2 negative 1 squared minus 3. These become, negative x. These become positive x's. So we have negative x 3x squared plus 1, 2x squared minus 3, which we see is not the same as our original function. Therefore, it is not even. Now, let's see if it is odd. So f of negative f of x. Sorry, I keep confusing that. We just multiply the first term by a negative, and we get 3x squared plus 1, 2x squared minus 3, and we see these two equal, therefore it is odd. Lastly, we need to sketch a graph of the function, so if we don't, let's quickly do that. The last question decided to persist. Okay, C. So we have the x-intercepts at 0, square root of 3 over 2, plus minus. And then we need to find f of 0. When the equation is equals to x 3, oh my, give me a second. Okay, I found it. Negative 3x squared plus 1, and then 2x squared minus 3. So we would have 0 and 0, you know, we immediately have our answer. Therefore, y is equals to 0. Let's graph this quickly. That is definitely a straight line. So we have this at 0, then we have a negative square root of 3 over 2, and then square root of 3 over 2. Again, you could expand these, but it might be a little bit too difficult for some of you. It's probably more beneficial that way, so that you know the exact zeros of the function. Like, for example, here, you could pretend this is a difference of squares and do square root of 2x, square root of negative 3, but those are not nice numbers, so you could just keep it at this, at what we did, and then at 0, it's 0. So let's just do this. We would have something along the lines of this, since our leading coefficient is positive, and then we have an odd, you go, and then, there you go. That is what our graph will look like. That is around it for today. Again, thank you to everyone who has tuned in for today's lesson. I hope you have learned a little bit more than you have known before, and I can't wait to teach you next time. Bye everybody.